This video is going to be for implicit differentiation. The reason that we're doing this video is because neither Ms. Schwartz nor I are in class for our first, third, sixth, and seventh periods. Please make sure that you're not making excuses for yourself if you don't understand the material after you've watched the video. Please make sure you use other references like Khan Academy, like the textbook, like any of the resources that we have available, so that way you can actually get the help that you need. On Friday, when we meet again, the expectation is that you know how to do implicit differentiation. How you got there, it's up to you. Just make sure that you're not making excuses for yourself. Again, I am taking the time to make this video, so what you can do to help yourself is not only follow along. Some students watch the entire video just to see what it is and then copy down the notes afterwards. Some students pause the video while they're listening to the while they're writing, just so they can catch up and process things that they're doing. And then other students will rewind the video and go back just to hear this part again, just to make sure they really understand the concept. Again, you are able to learn from a video, so please make sure that you are doing so. And we are going to start. We are on page 9 through 11 in your packet, so please go on and get that out. Page 9 through 11 is what we're going to do. You're not going to necessarily need your calculator right now, but you're welcome to have it out. Again, you know that there's no calculator portions of the test, so I would encourage you to not use the calculator unless you are explicitly told that you are allowed to do so. Let's go to page 9. So implicit differentiation. We have two warm-up questions in front of us. First, one warm-up asks us to find the equation of the tangent line. One warm-up asks us to find the derivative with respect to x. What I would recommend is going ahead and trying to solve those on your own. This is page 9. So please pause the video and try to solve the warm-up 1 and 2, and if you want to do it with your group, that's fine. Okay, I'm going to assume that you tried that one on your own, so here is the answer. I'm going to assume that many of you did it this way. You solve for y. Y is equal to the square root of 25 minus x squared. Once you solve for y, you might have rewritten it to 25 minus x squared to the 1/2. And when you did your derivative, the 1/2 comes down in front. You have to the negative 1/2. And then you also have this times negative 2x. Please keep in mind that that part was for the chain rule for the derivative of the inside. Rewriting it was probably a good idea. The 2 on top and the 2 on bottom cancel. And then you're left with negative x over root 25 minus x squared. Because the equation is asking for the equation of the tangent line, we can actually just plug in x equals 3. And when x equals 3, we find our slope is negative 3 over 4. And I hope that all that work is correct. We have negative 3 over 4 for the slope. So to write the equation of the tangent line, we have y tan is equal to negative 3 over 4x minus 3 plus 4. And that should be your answer. Some of us might have done this a different way, and I'm going to do that for you right now, which is a preview of what implicit differentiation is. Some of you might have done it this way. 2x plus 2y dy dx equals 0. And then plugging in 3, 4, we get 2 times 3 plus 2 times 4 times dy dx. When x is 3 and y is 4 equals 0. And then when we move this over, we get negative 6, because 2 times 3 is 6, and we move that over, so minus 6 on both sides, is equal to 2 times 4, or 8, so I'll just put 8 here. A dy dx, which means that dy dx, when the 0.34 is plugged in, is going to be equal to negative 6 over 8, which is negative 3 over 4. And then you write your equation of the tangent line. This is a preview of what we're going to be doing later. And if you knew this already, good for you. But this little part here is going to be the new part, why we put a dy dx. Again, I'm not asking you to do that for the warm-up, though. For the warm-up, this way would have been totally fine. And hopefully, again, you got negative 3/4. If you didn't, I'm going to guess that you messed up on the chain rule, or you messed up on the simplifying, or again, you might have made a mistake somewhere if when you were plugging in 3 for x. Okay, so that's warm-up 1. Warm-up 2 asks you to find the derivative with respect to x. I'm going to do this one for you, where y equals sine x. The way we could do this one g prime of x is going to be equal to, we need a product rule here. And let's just rewrite g of x because we can. X times sine of x. So it looks like we're going to need a product rule here, which is going to be x times its first times the derivative of the second. So s prime. That's going to be cosine x plus the second times the derivative of the first, which is going to be that. There's g prime. Okay. What the point of that was is you might have noticed that these equations, you may not have noticed that, these equations have something in common, and that is that there is a y involved in the problem. Usually, up until now, we always have equations in terms of x. This time we had an equation in terms of y. And when we have something like that, that's called explicitly defined functions. So when we only have functions that are in terms of x, those are explicitly defined functions. And let's write that down here. So functions that are only in terms of x, let's just type this here. Let's do 18. I'm not going to write it because my students tell me that my handwriting is horrible. Okay, so your function, hold on. Let's try that again. And explicitly defined function is in terms of one variable. Okay, an explicitly defined function is in terms of one variable, and that's what we've been working with. This entire course so far, all of our functions have been in terms of one variable. However, if you want to actually make calculus applicable, you'll soon realize that not everything is a nice parabola or a square root function. Sometimes we have functions that are curves. A prime example of that is the folium of Descartes. The folium of Descartes is this nice ribbon-looking shape. This curve has an actual equation, and the equation for that is going to be x cubed plus y cubed equals 6xy. Your efforts would be futile if you tried to solve for y directly. It would be impossible to solve for y directly. In our equations above in the warm-ups, we were actually able to get rid of the y. We were able to solve for y by itself. But in this case, in the x cubed plus y cubed equals 6xy, it is impossible. It's futile to try to actually solve for the variable. And if you're not sure what futile is, I'll look it up for you. Incapable of producing any result, it's pointless. Good. Okay, so x cubed plus y cubed equals 6xy. Your efforts are futile, they're fruitless. You will not be able to solve for y by itself. So if we want to find the slope of the curve at any point, because that's what calculus allows us to do, we have to have a new technique to be able to do that if we can't isolate y. So first of all, make sure you know implicit differentiation allows us to take the derivative of any expressions that contain more than one variable. In other words, you do not have to have your equation in one variable. So let's just write that down. You do not have to have take the derivative. Very, very important. And again, the term for that, if we are going to take the derivative of multiple variables at the same time, is called implicit differentiation. It's a fancy word. The differentiation part means derivative. The implicit part means implicit. That's not helpful. Okay, let's go on to the next part, and we'll see what implicit differentiation is actually. And then I think we will eventually take the derivative of x cubed plus y cubed. Yep, there it is. Okay, so let's go to example 1. I want you to listen very carefully to this, and I want you to watch it 55,000 times if you need to make sure you understand what I'm saying. When we write down d dx, because we've done that before, we usually have something here, and we say that as we are taking the derivative of something. From now on, we are going to take the derivative of something with respect to x. That last part with respect to x is what that dx means. The take derivative is the top part. With respect to x is what the denominator means. So in my example 1, and again, that's something that you need to make sure you know. So for example, for 1a, when I take the derivative of 4x cubed, well, I'm taking the derivative of 4x cubed with respect to x, and that makes sense. I'm going to get 12x squared. Okay, nothing new there. In fact, what I would actually get is I'm going to get 12x squared dx. And the reason I did that, because that's super weird, and I've never done that before, the reason I put this last part is this part is saying that now I just took the derivative of x of the variable x, and then the bottom part, I said I just took the derivative of x with respect to x. We don't usually do that for x's because you can see the dx over dx is just 1, so we would never really do that. But it really is helpful when we don't have x's all the time, and we'll see that in part B. So for the first one, we have everything that we need here. Whoa, hold on. Okay, so let's do B. Well, the derivative of 3y squared, we would proceed as usual. The derivative of 3y squared is 6y. But what did you just take the derivative of? Well, I took the derivative of y, and it was with respect to x. So let me highlight some things here. I took the derivative of y because there was y's in the equation, but I took the derivative of y with, different color, with respect to x. I took the derivative of y with respect to x. Again, the point of this variable here, and this is implicit differentiation, the point of this little dy dx is saying I took the derivative of y with respect to x. It's communicating to the person that you just implicitly differentiated. And when we say we took the derivative of y, we get dy dx, and that's really it. We have a few more problems to try here. So let's keep going. For C, the derivative of x plus 5y. Well, the derivative of x with respect to x is just 1. So this first part is just going to be 1 plus the derivative of 5y will be 5, because slope of 5y, so it's 5. But I just took the derivative of y with respect to, with respect to x. Sorry, I kind of burped. Okay, so that's C. For D, I need a product rule. So let's do first times second, derivative of second plus second times the derivative of first. Please pause the video if you want to try it on your own. And I'm going to get, the first one will be x, the second one will be y. I'm going to get x times, okay, the derivative of y cubed. Ooh, make sure you try it on your own. 3y squared, because that part doesn't change. The power rule will stay. The implicit part is just putting that extra little weird thing, the dy dx, because you just took the derivative of y with respect to x, plus the second part, which is y cubed. And again, we need a product rule here, so that's why I'm doing a product rule. It was x times y cubed. So plus y cubed times the derivative of the first, which is just 1. And again, I could put that I just took the derivative of x with respect to x, but that's just 1. So we don't usually write that. Oh, come on. Okay. So I'm going to actually erase that part. I'm just going to keep 1. We really only put that last part, that dy dx, if we are taking the variable, the derivative of a variable that is different than the one that we intend. That's your answer. You don't have to do anything with it. So to summarize, before we go on, when you put dy dx, that is implicit differentiation. because you are taking the derivative of a variable that is not explicitly defined, and you have to put that dy dx part. Are there any questions? Good, because now we're going to go on to the second example. Please pause the video and try to do that on your own.